In this video here, we're going to take a look at kinetic and potential energy. Now we can calculate the kinetic energy of a moving particle and also the potential energy of a particle. So for kinetic energy then, which we often just abbreviate to KE here, that is equal to 1/2 mv squared, where m is the mass of the particle and v is the speed of the particle. And for potential energy here, again, we just often abbreviate this to PE here. That is equal to mgh, where h is the height of the particle above an arbitrary fixed level. Now you do need to be aware then that a particle possesses kinetic energy when it's moving. And when the mass of the particle is measured in kilograms and its velocity is measured in meters per second, the kinetic energy is measured in joules. And you also need to understand here then that a particle possesses potential energy whenever gravity acts upon it. So when the mass of the particle is measured in kilograms, the acceleration due to gravity is measured in meters per second squared, and its height above the fixed level is measured in meters. The potential energy is also measured in joules as well. And just note here then that potential energy is negative if the particle is below the fixed reference level. However, kinetic energy cannot be negative. Okay, so it is important that you are aware of these two properties here, if you want to call them properties, right? So potential energy is negative, as we just said, right, if the particle is below the fixed reference level, but kinetic energy cannot be negative, okay? And the work done by a force which accelerates a particle horizontally is related to the kinetic energy of that particle. So in that case then, work done is equal to the change in kinetic energy. So let's just have a quick look then at how we can derive this result ourselves. So before we work through a couple of practice questions here on kinetic and potential energy, let's just take a quick look then at how we can derive this result here. So by using Newton's second law, that's F equals ma, and the Suvat equations, we can derive this result here. So F equals ma, right? This is Newton's second law. We'll call this equation 1 here. And we also have one of our Suvat equations. V squared is equal to u squared plus 2as. Let's just call this then equation 2. So what we're going to do here then is rearrange the constant acceleration formula. That's this equation here, equation 2. And what I want to do then is make A the subject. So if we do that then, nice and straightforward here, right? All I need to do then is subtract u squared off both sides and divide through by 2s here. And if we do that then, we obtain the following. So what I'm now going to do here is substitute this rearranged equation into Newton's second law, F equals ma, okay? And if we do that then, what we obtain here is F is equal to m times v squared minus u squared over 2s. Well, if we times through by s then, what we obtain here is Fs is equal to 1/2 mv squared minus 1/2 mu squared, as required, right? That's what we wanted to obtain here. And just note then that work done is equal to the final kinetic energy minus the initial kinetic energy, which is simply the change in kinetic energy. Okay, so as you can see then, deriving this result here is pretty straightforward. So in terms of an introduction here to kinetic and potential energy, we don't need much more than that, so I think the best way to demonstrate this concept then of kinetic and potential energy is just run through a couple of practice questions. So let's just get started then with question 1 here. So let's just get started here then with question 1. So as we can see then for question 1 here, right, there isn't really too much going on. All we've got here is a particle of mass 0.5 kilograms that is moving at a speed of 20 meters per second. And all we want to do here then is just find its kinetic energy. So a nice easy question here, right? So don't forget then that for kinetic energy, I'll just shorten this to K.E here for kinetic energy. This is simply found by using 1/2 mv squared. Okay, so m here, that is the mass of, in this case, the particle, so that's 0.5. V is the speed that it's moving at, which is 20 meters per second here. So altogether then, nice and straightforward here, we simply get 1/2 times by the mass here, which is also 1/2. And then we times this by v squared here. So v then is 20, we times that by 20 squared. Okay. If we evaluate this here then, 1 over 2 times 1 over 2 is 1 over 4. 20 squared is 400. So I've got 1 over 4 times by 400. And if we evaluate that here then, nice and straightforward, we simply get 100. And don't forget our units here as well, right? We're talking about kinetic energy here. So our units are joules. Okay, so we get 100 joules there. And there we have it. So nice and straightforward. That simply gives us the solution to question 1. So moving on to the next question here, then let's just have a go at question 2. Now, as we can see then for question 2 here, there's a little bit more context than the previous question, but again, nothing too challenging. So what do we have here then for this question? Well, we have a box of mass 2 kilograms that is being pulled across a smooth horizontal surface by a horizontal force. We're told that the initial speed of the box is 2 meters per second and its final speed is v meters per second. We're also given the work done here by the force, right? And that is 1.75 joules. And all we want to do here then is find the value of v. So, like we said, right, pretty straightforward again. So to get us started here, we're going to use the fact that work done is equal to, so work done is equal to a half mv squared minus a half mu squared. Okay, so the work done here is 1.75. So 1.75 is equal to a half times the mass here, which is 2, times by v squared. Now, obviously, we don't know what v is, right? That's what we're looking to solve for. So times that by v squared minus m, a half, times by m, where again, m is just 2. Now times this by u squared here, where u is 2. So we times that by 2 squared. Okay. So 1.75 is equal to, so a half times 2 is just 1. So I've got v squared, because 1 times v squared is obviously just v squared. We've got v squared minus them. So a half times 2, again, that's just 1. Times that by 4 here, because 2 squared is 4. So I've got minus 4 then, like so. Well, we're looking to solve for v here, right? So just add 4 to both sides. In that case, then v squared here is equal to 5.75, like so. And then finally here, right, we just want v. All we need to do here then is just take the square root of both sides here, okay? So v is equal to the square root then of 5.75, like so. And if I give my answer here to, say, 3 significant figures, what I get here then is 2.40. Okay, that's 23SF there. Okay, and again, hopefully that was pretty straightforward, all things considered. That gives us the solution there to question 2. And then finally, to finish with here, we have the very last question, question 3. So for question 3 here, as we can see then, we have a box of mass 5 kilograms that's pulled 8 meters up a plane inclined at an angle theta to the horizontal, where tan theta is equal to 3 over 4. It says, assuming that the box moves up a line of greatest slope of the plane, calculate the potential energy gained by the box. So, as we can see for this question here, right, we don't have a diagram. I do think drawing a diagram here is helpful for this question. So, let's just start then by drawing our own diagram. Now, it doesn't have to be perfect, by the way, just so we can visualize this problem. So what I've got here is the ground, right? My flat horizontal surface, like so. And we also have the inclined plane here, okay? Let's just say something like this. I've got my angle of inclination here, which is just given as theta, like so. I've got my box here. So I just kind of shade that on here. Something like so. I know from here, this point at the bottom, so that's where the box here starts, up to this point here is 8 meters. So we'll put that on our diagram here, like so. So 8 meters then. And what I'm also going to say here then, because when I'm talking about potential energy here, I'm going to say that the ground here is the 0 level, okay, or is our 0 level. Like so, okay? I've also got the mass here of the particle. So I've got the weight here acting directly downwards. That's 5g. So 5g newtons there. Am I missing anything else here? I think at this point, that is absolutely fine, right? What I also know here is that tan theta. So tan theta is equal to 3 over 4. And in that case then, if tan theta is equal to 3 over 4, what we can do here is form a right angle triangle, okay? And if tan theta is equal to 3 over 4, well, that is opposite over adjacent is equal to 3 over 4. So I've got my right angle here and my angle theta. In that case then, my opposite here is 3, my adjacent is 4, and in that case then my hypotenuse here is 5. And from here then, we can derive that sine theta, that is opposite over hypotenuse, that is 3 over 5. And cos theta here, that is adjacent over hypotenuse. That's 4 over 5 there, okay? We might not need these, but I would assume at some point in the question, we will need probably one of these, right? So what else can we kind of work out here? Well, what I'm looking at here then is potential energy, right? So I'm going to consider this in 2 stages. I've got the initial potential energy and also the final potential energy. Now for the initial potential energy here, so for the initial potential energy, this would simply be 0. Okay, I don't know why I've kind of written it all out in full, but we'll just roll with it. So the initial potential energy here, this would just simply be 0, right? Because the starting point here, this is my 0 level. So the initial potential energy, which I'll just show on to P dot E here. I don't know why I did it in full, but it doesn't matter. Like I said, that's just simply 0. Okay. Now, I also need the final potential energy here, but before we can work out the final potential energy, I also need the change in height. Okay. So for the change in height here, let's just state this underneath them. So for the change in height here, what I need to consider then is some basic trigonometry here. If I consider this situation, this scenario here, and I draw a right angle triangle, something like this, that's supposed to be right angle, but again, doesn't matter too much. My diagrams are never perfect. This length here, the hypotenuse is 8 meters. I've got my angle theta here. So this side here is the opposite. This side here is the hypotenuse. And then this length here at the bottom is the adjacent, right? So in that case then, what I've got here is that sine theta. If I just call this side here h, for example, because that's what we want to know, right? The change in the height here. So from this point to this point, I want to know what that is. So if I call that h then, h here, well, we evaluate that by using trigonometry, right? So in that case, sine theta is equal to the opposite over the hypotenuse. So the opposite here is h over the hypotenuse, which is 8. So sine theta is equal to h over 8, and then just rearrange here for h, right? And in that case, then h here is 8 sine theta. Okay? And sine theta then, as we evaluated here, is 3 over 5. So the change in height then, that is given as we just said then, 8 sine theta. So 8 sine theta, which is equal to 8 times 3 over 5. Okay? Evaluate this here then on your calculator. What we should find here then is we get 4.8 meters. So I know here then that the change in the height is 4.8 meters. So altogether then, for the final potential energy, I will shorten this one. So final potential energy here, that is equal to mgh. So mgh. So m is the mass here of 5 times by g, which is 9.8 here. And then we times that by h here, which as we just evaluated is 4.8. Okay. Like so there. And in that case then, just put all this here into your calculator. So if we just quickly do that here, what do we get then? So 5 times 9.8 times 4.8, That gives me 235.2 there. So 235.2 there. Okay. And don't forget here then, this is potential energy. So my units here are joules. And in that case then, to finish with here, the potential energy. So the potential energy gained by the box here to three significant figures here would be 235 joules there. Okay, so 235 joules there. Okay, and there we have it then. So like you can see, a little bit more complicated there for question 3, but again, mathematically, nothing too challenging, right? Just a bit of basic trigonometry. So there we have it then. That gives us the solution here to the very last question for this video, question 3. And that brings us to the end then of this video here on kinetic and potential energy.